I remember the last time I was an organizer of this school, the COVID started. It was just the time when COVID started in Italy, so it was quite an interesting time. So your colleagues were here, and we had to stop the school and send everybody home because of the outbreak of COVID in the end of February 2020. So it was not an easy time then. So I hope that this school will end in a better way, since I'm still here as a lecturer this time. And my task, the task I've been given from the organizers, is to tell you, in a sense, the point of view on relativistic hydrodynamics, which is one of the main tools of heavy ion physics, which is more suitable to deal with quantum phenomena, first of all, and for the new observables, especially spin polarization, which emerged as a very interesting subfield of heavy ion physics since it was observed in 2017. It was predicted to be there, but it was measured in 2017 by the STAR experiment at BNL, and it has become an interesting topic itself ever since. I don't know if I will, my program is to, say, introduce this point of view, so the basic tools of quantum statistical mechanics in the relativistic framework to understand, so how to calculate this phenomena, but I don't know if I will, say, manage, since I have a limited time, to show you how to do this, so how to extract the formula of spin polarization from this formalism. However, I hope that eventually you will be able to do it on your own. So that is my, my intention. Secondly, I would like, for starting, to mention that I'm very honored to be a lecturer here, because this is the very place, as the director of JGI mentioned, this is the very place where, in a sense, the first quantum thermodynamics began, because that is the place where Fermi wrote his paper on Fermi statistics in 1925 or 26. And at that time, I think I have, maybe I have it here, but he wrote a paper where his affiliation was simply Enrico Fermi von Florenz, because at that time the language of physics was German, so he submitted this paper to Zeitschrift für Physik. And he didn't write University of Florence, simply because there was so this institute was not still part of the University of Florence. So he wrote simply Enrico Fermi von Florenz at that time. Very interesting. If you, these days, if you got if you are an editor, you got a paper, you get a paper from somebody writing Enrico, some name from Florence, you simply reject it. There's no affiliation, quite suspicious. Okay, so let me start with saying something about the traditional approach to relativistic hydrodynamics. So my first lecture will be devoted to an introduction to the usual approach, say the classical relativistic approach to the hydrodynamics, which is still the most popular among the physicists in our field. And the hydrodynamic model, as it will be explained more in detail by my colleague, Mike Strickland, has been very successful in describing relativistic heavy ion physics. And what I mean very successful, it means that it has been successful in describing the data. So the spectra of particles, the anisotropies, as it will be shown, and many other observations. If I draw a diagram of space-time, so if you have coordinate Minkowski space-time of the space-time, relativistic heavy ion collisions is usually sketched in this diagram as with the two lines defining limiting the light cone, with the two nuclei which are moving at almost the speed of light. They interact here in the 0 point. Okay, and then what you have is the formation of what happens here within the light cone is the formation of what you believe it's going on is the formation of a quark-gluon plasma. Quark-gluon plasma lives, of course, within this region of the space-time, okay? And in a portion of space and time, until it, as you know, it cools down and expanding, breaks up into hadrons. And we have a 3D hypersurface, which is usually of that shape. Hypersurface means three-dimensional submanifold of space-time. So, for instance, you can think of our Euclidean space, where the quark-gluon plasma falls apart, ceases to exist, and it gives rise to hadrons. So the quark-gluon plasma lives in this region here, from some unknown or almost unknown, starting point, so hypersurface, 3D hypersurface where it is formed, and then it evolves, it cools down, and then it produces particles which then have their own world lines flying to the detectors. The hydrodynamic models tries to describe this portion of the space-time, so what happens within here. And it tries to do this by using a limited amount of information. So it tries to describe by using the stress energy tensor. I hope that you are familiar with basic notions of relativity, which describes the density of energy, momentum, and the internal forces of a continuous medium, and possibly some currents, like the electric current, the baryon current, so currents of conserved charges. And it tries to do this by simply solving these two differential partial equations. So by solving these partial differential equations, tries to determine what happens from some initial conditions, of course, to some final state. Initial conditions are usually, in a relativity problem, are specified on some 3D hypersurface, which is of space-like. What do you mean? What does it mean, space-like hypersurface? It means that this is a hypersurface of space-time, so a region with submanifold, 3D, which has as a normal vector a time-like vector. So it means that its normal vector, it's time-like. This is a 3D hypersurface. This is a very important, usually labeled by a capital sigma, very important notion. So relativistic hydrodynamics, what it can do is that once you know the conditions of the fields at some hypersurface, sigma, then you know what happens at any other future hypersurface. It's a deterministic system. Okay? This is called a Cauchy problem. in the relativistic jargon. So you have to know what happens, you know, have to the conditions of some fields, the fields which are the unknowns of these equations at some hypersurface, then you can predict what happens later. In the relativistic heavy ion collisions, the usual hypersurface, the initial conditions, is a hyperbola. It's a space-like hyperbola like this. This is what is usually chosen in the so-called Bjorken model. So we presume, although we don't know, so that there is no, say, we have not a knowledge from the data, but we say the model presumes that we know the initial conditions over a space like hyperbola. Okay, so how then you can imagine, so if you look at these equations, you say, okay, but how can I solve this equation? How can I determine what happens? So how, is this really a deterministic system? Because if you count the number of equations here, how many of them? There are 5, right? There are 5 because you have 4 indices here, and you have, yeah, this is just saturated, so this is just one equation. So you have 5 equations. So in order to make this system deterministic, you need to have 5 unknowns, 5 functions. Otherwise, they would be. And these 5 functions are, in the relativistic hydro, usually a 4-velocity field, u mu, which includes only 3 unknowns. The reason being that u, being a 4-velocity, must be normalized to 1. And 2 more, so you are now left with 2 more unknowns, and these unknowns are, so how to go down to the 2 unknowns? Well, the point is that if you 2 unknowns, you may have only 2 unknowns to describe the system, only if you resort to the notion of, to resort to thermodynamics. Because only if you assume that you are close to a condition of, and you will see why I'm saying close, of local equilibrium, local thermodynamic equilibrium, you can pick up only 2 unknown functions to describe the whole evolution. And these unknown functions are usually temperature and chemical potential, which is associated to this conserved current. Okay? Or you may describe with 2 other different thermodynamic functions. For instance, you may see in some textbook that you may describe the system with pressure and energy density. But then pressure, energy density, and some charge density. There are 3, okay? You have 3 unknown functions, so there must be a relation between them, which is called the equation of state. So ultimately, what you need is thermodynamics. So you need to describe, in order to describe the system, you need to have a temperature and the chemical potential, so, or some 2 different functions, but nonetheless, there must be a relation which is dictated by thermodynamics. Otherwise, it would be impossible to solve this system, except in special cases. For instance, in the conformal case, you may, maybe, I think that this will be discussed in the afternoon lectures. It will be possible to describe the system, to describe the deterministic system evolving. Okay? Now, now I have to, yeah, now let me show. So how to turn now this stress energy tensor and the current into these fields? So what is the relation between the stress energy tensor and the 4 velocity? What is the relation between the stress energy tensor and the temperature and the chemical potential, so that I can have only 5 unknown functions and then solve the system. Let me show you, so it will be very long to do it by hand now at the blackboard, so let me show you some notes that you will see here on the screen. Sorry? Well, this is a this is a good question. And you know, I would like to write some notes for the school. That the problem is time. I don't want to make a promise, but I will try to make my best to write some notes, which will be able online. They are not at the present because for the present there are no notes written. Yeah?
The draft will already be perfect itself like this.
What?
The draft itself, these notes handwritten, will be already perfect.
These notes?
Yeah.
Okay, yeah. So there are no comments, but of course this will be made. These notes, which are very simple, no comments, will be absolutely made available. Yeah.
Thank you very much.
Okay, no problem. Oh yeah, okay. I didn't say this, but you are free to interrupt at any time. Yeah. If you have a question, please don't hesitate. Just like your fellow. Okay, these are notes that. Is there a stick here? Not a pointer. Let me see. Yeah. In these notes, summarize what is the traditional method to achieve to install, in a sense, or to create this relation between the stress energy tensor, classical, yeah, this is a classical field, depends on X, and as well as the current, and a four velocity field. Well, one of the differences between relativistic hydrodynamics and classical hydrodynamics, in the relativistic hydrodynamics, it's very easy to realize that the four velocity field is somewhat arbitrary. So there is no really unique underlying velocity vector like what we were used to learn in classical hydrodynamics. And therefore, the traditional, I would say, approach does not specify what is physically the four velocity vector. It simply says that if you have a time-like normalized field U, okay, which you can call four velocity, you may decompose T mu nu, so a generic symmetric stress energy tensor onto U, okay, in a very general way. So assume that you have this time-like field, U, which is normalized, regardless of what it is, okay. What you can do is at any time, at any point X, so I have omitted the argument of X for the sake of simplicity here, okay. But you can decompose T mu nu onto U and onto the hyperplane orthogonal to U in this way. This is a very general decomposition. So any symmetric stress energy tensor, like any symmetric tensor like the stress energy tensor can be decomposed onto U in this way. This rho prime, P prime, Q, and pi are simply projections of T mu nu onto U. So in a sense, you can reverse this, and you say that you can define these, say, tensors and coefficients and vector fields starting from T and U. For instance, you can define rho prime this way, you can define Q mu this way, you can define pi mu nu this way, and P prime this way. And then, of course, you can invert the relation and write T mu nu as a function of these newly defined fields. Well, it is important to point out the meaning of this of the symbols here. U, as I said, is to be understood as a four velocity field. Delta is the projector onto the hyperplane, which is orthogonal to U. I think it can be written in relativity like this. So imagine that U, X at each space-time point defines, of course, a hyperplane, or a 3D hypersurface, which is a hyperplane, which is orthogonal to it. and delta is the projector onto this hyperplane, okay? Is a projector, meaning that if you compose that, you can show this, but it's a very simple exercise, that delta mu alpha nu is equal to delta mu nu again, so it is idempotent. Now, this pi mu nu is the, so P prime is the contraction between delta mu nu and T mu nu, and therefore P mu nu turns out to be so-called traceless. It means that if you contract this P mu nu with delta mu nu, you get 0. Also, from this definition, it turns out that Q dot U is equal to 0, and U mu pi mu nu equal pi mu nu is equal to 0. So they are orthogonal. Pi mu nu is orthogonal to U for both indices. So the same game can be played with J mu. J mu can be decomposed. This is more easy. This is easier because this is a vector field. Can be decomposed as onto a vector which is can be decomposed along U and orthogonal to U, this way. So all of this, no, the point is here, I have used these symbols, rho prime, P prime, and N prime, not by, say, not by chance, but just to emphasize the difference. This formulation of relativistic hydrodynamics is very similar, or is inspired by classical, or say, very well-known papers by Israel in the 70s. What is required is the following, is that U is arbitrary vector field. But when we come to the global thermodynamic equilibrium, so imagine that you have this fluid described by T mu nu and J mu. Then, of course, this fluid can achieve, in principle, could achieve a global equilibrium, thermodynamic equilibrium. And it means that at global thermodynamic equilibrium, as you will see that there are different forms of it, but in the simplest form, global thermodynamic equilibrium means, or a special form of global thermodynamic equilibrium is when U becomes a constant, means that it is the same for vector at every point in space and time. This is the so-called homogeneous global equilibrium. It is the simplest form of equilibrium. What happens when U becomes a constant for vector? So when global thermodynamic equilibrium is achieved? Well, what happens is that T mu nu should reduce to this form, okay? To a form where you have only two independent coefficients, so and not a vector field and a tensor field, but just two coefficients, rho and P, of this form, okay? So that means that this Q and pi, when U becomes a constant vector, should vanish, okay? And similarly, for the current, what should happen is that it should reduce to this form. These forms are dictated by symmetry. So there is no physical assumption here. Every symmetric tensor should be of this form at global equilibrium. This is an implication of the symmetries of global thermodynamic equilibrium in terms of isotropy, translation, and so on, okay? Also, rho and P should be constant, so all of them should be independent of X. Rho, P, and N are the thermodynamic equilibrium functions. So in this situation, we are in the rho, P, N should be determined by two parameters, because we have a homogeneous situation. These two parameters are the temperature and the chemical potential. And also there must be a relation between rho P entropy density and the charge density, which is the usual thermodynamic relation rho plus P equal Ts plus Mn. Of course, when you are at global equilibrium, you can replace this rho, P, S, and N with the total energy, the total, PV. You can replace the total entropy and mu n, so this becomes the usual, thermodynamic relation, global. In this case, since there is no dependence on x, then we have this relation which is also local, so applies to the densities, to the proper densities. Now, now here comes, so this is a form which is at equilibrium, but what happens if we are not in equilibrium? If you are not in equilibrium, then there is no reason why, in principle, this rho prime and p prime, so the coefficients that I have defined here as a decomposition onto the four velocity field, whatever it is, there is no reason why they should be equal to the what? To the equilibrium functions at x. So something which is determined by a temperature and the chemical potential field, but with a functional dependence which is the same as at global equilibrium. So imagine that you have your energy density which is determined by T and mu with some relation, for instance, rho proportional to 10 to the fourth. This would be for the massless particles. Well, okay, so you can, so if you are in a situation where you can define T and mu at every spacetime point x, then you can take the same functional dependence. So you can take rho of x as a function of T of x with the same functional form. So this equilibrium x, rho equilibrium x means that this is the thermodynamic function which is a function of the T and mu at the point x. Okay? And similarly, I can do the same for the pressure, for this P prime here. Okay? If I compare this formula with this formula, then okay, I have written this say by not using the delta projector, but this is essentially, it is basically the same. So you can define a non-equilibrium pressure in a sense, which is the difference between P prime and the function P equilibrium of x. And similarly, you can define a difference between the charge density in a non-equilibrium situation and the function of the equilibrium function of T and mu at equilibrium with T and mu depending on x. In the next slide, this will be disregarded for the sake of simplicity. So this is a basic, this is, say, the first basic step in order to calculate, in a classical relativistic approach, the so-called constitutive equation. So what we do not know so far is what are Q and pi. So how to determine the unknown part, or if you wish, how to determine the non-equilibrium part of the stress energy tensor, okay, in order to, eventually close the system and try and being able to write a partial differential equation which can be solved. In order to do this, you need to have the so-called constitutive equations. So some equations which relate Q and pi as a function of the four velocity. And this is the sketch of how this is obtained. This is a traditional approach, okay, which relies on essentially on keeping the validity of thermodynamic relations even in a non-equilibrium situation. So it means that what we will do in the following will be to retain the validity of this formula, retain the validity of this basic thermodynamic differential relation, which says simply that the derivative of entropy with respect to rho is equal to 1 over temperature, the derivative of entropy with respect to the charge, the density of charge is equal to minus mu over T, which is what you learn in thermodynamics, okay? So if we keep the validity of these equations point by point, what we can write the gradient of this energy, the entropy density, as a function of the gradients of mu of rho and n, of the energy density and the charge density, And eventually, after having defined this symbol, dot as the longitudinal derivative, so this is what you get is that we will be able to write some constraints that will tell us how Q and pi will then eventually be determined in terms of the four-velocity field. And this is what will follow is the method. So the method starts with writing, first of all, the mu t mu nu equals 0. So enforcing, of course, the equation of motion. Okay? And then plugging in the decomposition of t mu nu. So we have this decomposition, okay? We plug it in with this definition of delta rho, pi, and delta n, okay? Delta n has been disregarded, as I said, otherwise would become really cumbersome. So if you then use this decomposition here, then you can write these partial differential equations. And the second step is to contract this with u nu. So just doing this. And if you contract with u, there are some terms which drop simply because, for instance, you encounter some derivative like this. All terms involving u nu, the mu u nu, they simply vanish. The reason is being that this is equal to 1/2 the mu u squared, which is equal to 0. So you are left with all these terms, okay? Again, let me go through them quite quickly. And then you have that you can replace all the longitudinal derivatives with just for using this shorthand, the rho dot, p dot, okay? What happens here, let me also emphasize this. It appears for the first time a very interesting field, which is the following. This is the derivative, longitudinal derivative. So this is a derivative along u of u itself. And you can show that by using some word line as an example, that this coincides with the four acceleration field. So this has a very meaningful content. And then you are left with this contraction of derivatives. For instance, you can use the Leibniz rule to show that this term is the mu u nu pi mu nu, which is 0, minus pi mu nu the mu u nu. So this is just very simple manipulation, okay? But let me go through. Finally, all of this has the goal of obtaining rho dot. So if you contract all of this work, so contracting with u nu, so reducing these conservation equations to just one equation, has the goal of obtaining the longitudinal derivative of rho, which turns out to be quite complicated. It involves, you see, the divergence of Q, which we don't know what it is, Q dot A, and then you have this column means this is a double contraction of pi with the gradients of u, and then it's more, okay? You can play the similar game with the current density. Here, there is no need to contract with u, just to take the divergence. And eventually, what you get is that you can obtain n dot. N dot equal minus n divergence of u minus divergence of j. Here, I emphasize that I removed the delta n, so-called, okay? And why did I do this? Because eventually, what I want to obtain is Ts dot. So I want to obtain rho dot and n dot and plug them into the thermodynamic relations, the thermodynamic differential relation. And so eventually, what I get is that I take the thermodynamic relation and I take this equation and I put them in. What I get is that an equation which tells me how large, or so tell me what is the derivative of entropy, the longitudinal derivative of entropy in terms of the unknown components of the stress energy tensor and the current vector field. I confine myself to just one current vector field, but I mean, without any, you can imagine that without any problem, I could do this for n conserved currents. In heavy ion collisions, for instance, you know that there are at least 3 relevant conserved currents: electric, baryon. Okay? All these calculations, I just took one sample current, but believe me, it will be very straightforward to extend this to an arbitrary number of conserved vector currents. Yes?
If the currents couple to each other, is that simple? If you have like 3 currents that are coupling to each other?
Well, they are independently conserved. That is the point. So they are not coupled in the sense that the divergence of the baryon current, the strange current, and the electric current should be equal 0, regardless of there is interaction between the particles carrying these charges. So it would be like it would be similar. There is a complication, though, as I mentioned, that I forgot this out of equilibrium, this non-equilibrium part of the densities in these calculations. But it should not be difficult to extend all of this. This is because the reason is practical. I mean, if I had to include them, that this will become larger than the size of the paper, the size of the sheet. However, I mean, it does not really add much to what the message I want to convey. So altogether, then you can manipulate this, eventually show that you get, that's a very important point, you get something which is the entropy density itself, okay? If we go back to this equation here, you see, okay, that Ts rho plus P minus mu n, and then if you look at this expression here, that is just minus Ts, okay? So you can replace this minus temperature times entropy. And then you have other terms here, okay? All of them including something that we don't really know. So we don't really know what is Q, what is pi, what is little pi, what is delta rho, and what is capital J. All of them are, we only know that they are non-equilibrium fields. Now, what I can do is then I can take this and I can carry this to the left-hand side, okay, and divide by T. And what I get is that S dot plus S entropy times the divergence of U, which altogether I can write like this, the mu SU mu. Okay? The reason is, well, I think we have S dot is equal U mu then mu S. Okay? So if I sum U mu then mu S plus S then mu U mu, this is equal to the mu SU mu. Okay? And here what I do is that I use the Leibniz rule to express this divergence of Q divided by T. So this T is just because I had a temperature here, so I had to divide both left and right hand side. Okay, I can use the Leibniz rule to, for instance, to write this minus the divergence of Q over T plus Q dot derivative of 1 over T. Okay, I can left this, oh, sorry, there is a T missing here, but I can correct online. Okay. Then I have all of this, and I can make the same, apply the same Leibniz rule to this term here, and leave this unchanged. So eventually I get the mu as mu equal minus divergence of q over t plus blah, blah, blah. Okay, and all the divergences of some vector field, like this, and this, can be brought to the left-hand side, and eventually I get some equation which tells me that the divergence of SU plus Q over T minus mu over Tj plus the rho, delta rho U over T is equal to, and here on the right-hand side I have the product of vector fields with vector fields, tensor fields with tensor fields, or scalars with scalars. Okay? This is the basic equation which is used to obtain the constitutive equations, because I can call this entropy current. This is the divergence of something which is defined, if you wish, as S mu. Okay? And this, the mu S mu, so the divergence of the entropy current is given by the product of vector fields with vector fields, each of them involving a gradient. For instance, here we have the acceleration itself, as I told you, involves a gradient. We have the gradients multiplying pi, the divergence of u multiplying, this is a scalar multiplying this non-equilibrium pressure. And then we have the known, say, this is called diffusion currents, multiplying the gradient of chemical potential at temperature. And also here we have delta rho multiplying the longitudinal derivative of temperature. So all of them have the same structure, and on the right-hand side we have the divergence of an entropy current. So we have in other words, we have the mu S mu equal something, and now comes the physics principle. You know, the physics principle says that the mu S mu should be always positive. This is the second law of thermodynamics. In relativistic form, which means local. So the second law states that this is always positive, not strictly, but should be either positive or equal 0. Okay? This is the only way the second law can be implemented in a relativistic framework. Because in a relativistic framework, everything should be local, okay? So it would not make sense, or it would be very difficult to talk about some global increase of entropy, simply because global increase of entropy, if you think of, for instance, two, what does global increase of entropy mean? But if you think about it, it means that the entropy in the past must be smaller than the entropy in the present. But what is the past and the present? Of course, this depends on the state of the observer, so the velocity of the observer. What is past for something, the past is always past, okay? But in order to make it, say, really properly relativistic, the second law should be implemented locally. And this is the way that in relativistic hydrodynamics or thermodynamics, the second law should be written. So that the mu as mu is always positive, okay? The divergence of the entropy current is always a number which should be larger than 0. And in fact, this is, we will see this, that the entropy, global entropy relativity, can be only expressed in this form, so just by an integral over some 3 some hypersurface of a current. Okay, there's another way that you can express some scalar which depends on time. Okay, it's like the charge in relativity. It can only be expressed in a covariant way as an integral of a vector field which is a current. Only in this case you can talk about something which is global, okay? Now, so this is a very important equation, and therefore, so an equation which comes from a physics principle. This is not something which can be deduced, so this is an input, okay? Physics input, very important. And so what this means is that all of those terms should be positive. And I mean all of them, because you can imagine a situation when one of those gradients is simply 0, okay? You can, for instance, turn them off one by one, except the only one you are interested in, and then conclude, therefore, that this term should be positive. Okay, so for instance, what I can do is that I can turn off the acceleration field as well as the gradient of temperature, but I can leave this on. So I can imagine a situation where I have a velocity field which has a gradient, so acceleration is 0, but nevertheless, this is different from 0. And all of them, for instance, then I can imagine that all the other gradients are 0, and therefore, by focusing on one of them, I can conclude that they should give a positive contribution to the entropy increase. And in this case, for instance, I would conclude that this is the easiest way to achieve positiveness is that pi is itself proportional to the gradients in order to give me this a quadratic term, which is positive, because in this case I would have something like du over du. This is double contraction of any tensor field itself will give us a positive contribution, okay? Let me give another example. Suppose that all of these terms, all of those are 0, okay? So how? I mean, I can choose a situation where I have, for instance, no gradients of the temperature, no gradients of the chemical potential of temperature, no gradients of velocity, except that, oh, sorry, no gradients of, oh, this would require some more elaboration here, in fact. But imagine that I have just acceleration. So I create some configuration of the velocity field and the temperature field such that only this term survives, okay? Well, in this case, I have to admit that this should be positive, always. Because otherwise I would contradict the second law. And how can I achieve this? I can achieve this by simply stating, here I wrote it in a more precise way compared to this very loose reasoning. In this case, the conclusion is that Q should be proportional to the acceleration and the gradient plus the derivative 1 over t, if it is there, through a coefficient which is positive, okay? This is because if I have this is because this term would become Q times, and then would be minus Q over K, okay? So if I replace this equation in here, then I would get the mu S mu equal Q dot minus Q over K. This becomes minus Q squared over K, okay? Why is it positive? Does anybody know why minus Q squared over K is positive? Exactly, so okay, good, very good. Because simply Q dot U is equal 0, therefore Q is space-like, and therefore minus Q squared is positive, okay? So this equation ensures that that this term is positive, and therefore I have obtained, as a result, that automatically, under any circumstance, that the entry production is positive. And I can repeat this argument for all other terms. And by doing this, what do I obtain? I obtain something very interesting, because I obtain a relation between the unknowns, okay, unknown terms of the stress energy decomposition and the gradients, in this case, of the fields of u, of t, and mu. Okay, and this allows me to close the system. Okay, so finally, it allows me to write t mu nu as a functional. So it means that it depends not just on u, but also on derivatives of u, and on t and derivatives of t, and mu and derivatives of mu. Okay, of t mu nu and j mu, and therefore now I have 5 partial differential equations for 5 unknowns. Yes, please.
I have 2 questions.
Yeah, please.
Maybe I'm a bit lost, but what is the Q again? Exactly.
What is Q? Yeah, Q, I have not mentioned this from the physics point of view. I have just mentioned that in this, say, traditional theoretical approach, sorry for, let me see if I, okay. In this traditional, theoretical approach, Q is a projection, okay, is a projection of t mu nu onto the 4-velocity field on one hand and orthogonal to it. So you have 2 indices. So you project onto u on one index, and then you project onto the hyperplane orthogonal to u on the other index. The physical meaning, what is the physical meaning of Q? Well, the physical meaning of Q is implied in this constitutive equation, okay? So eventually what you find out is that Q must be regarded as the relativistic extension of what in classical relativistics, in classical thermodynamics, in classical hydrodynamics is the so-called heat current. The heat current, yeah. Well, maybe among this, maybe I would, so I think that the time is up. For, yeah. I recommend to you to a book by let me see if non-equilibrium thermodynamics. This is a very interesting book where you can find an account, very complete and very profound account of classical thermodynamics, of classical non-equilibrium thermodynamics. So when you have densities and you will find this vector many times, the heat current, okay? Yeah. Yeah. No, well, I mean, depend. Okay, where you change the velocity, but you change. Yeah, I think so. Yeah, you can divide. I think you can imagine a situation where you have a gradient of velocity and a gradient of temperature which is 0. Although that is in classical, say, classical hydrodynamics, you can do this. In relativistic hydrodynamics, I don't know. Well, I would say so, but I would not take this too seriously in a sense that should be checked. Because I'll tell you why. Because in relativistic hydrodynamics, as we will see, I don't know if there will be enough time to do it, that you may have a global situation where temperature is not constant. Therefore, to make the, actually what you can make, you can, for instance, you can, in relativistic hydro, in relativistic thermodynamics, you can make this equal 0 by simply enforcing that the 4 temperatures are Killing vector. So this is easy to achieve in a sense. So this is a sort of signature of global equilibrium. But I don't know if you can do it in a non-equilibrium situation. That is a very good point, but yeah, maybe we can talk about this in the afternoon sessions. Okay. Anyway, so the main message is the following, is that by using this method, this is what traditionally so this is the way that constitutive equations are traditionally achieved. You can find out what is the physical meaning of these projections onto this full velocity field, okay, q and pi, which at the beginning were not defined. Okay, by using the second law of thermodynamics. Okay, there are many open questions, okay, on this method, and I will tell you one of them, or some of them, in the next fraction. I think it's time to stop and have a minute's break. And so, is it okay resuming at 12:30? If you have questions, please, I'm here. Okay, so I think I can resume. So what you have seen in this first part of the lecture is the traditional, I would say, approach to relativistic hydrodynamics, which eventually leads to finding the so-called constitutive equations, which involve the appearance of, so that involves the appearance of the non-equilibrium terms, or often called non-ideal terms, which are proportional to gradients of the velocity fields, of the temperature, of the chemical potential, and by comparing with the classical hydrodynamics, we also discover that these coefficients, so what is the physical meaning of the coefficients? For instance, I showed you one, which is Q. Q is proportional to the gradients of acceleration and gradient of temperature, and it's by comparing with the non-relativistic limit of these terms, we find that kappa, the coefficient here, has the meaning of a thermal conductivity. And similarly, we can obtain constitutive equations where the coefficients multiplying the gradients have the meaning of a shear viscosity, which will be mentioned, I think, several times in the lectures by Mike Strickland, and the bulk viscosity, and so on. Okay. Also, I left here something which is not usually found in the textbooks, which is this term here, which in principle, oops, I think that it's running out of charge. What is? Can't find. Okay. No, it's running out of charge. Yes, I think its batteries are gone. Yeah. Okay. Now I think I have to go. But this term it cannot. This term it is say not usually found in textbooks because, for instance, in the well, maybe I can postpone this discussion to later on. Okay. Now here, as usually, when we find something that this raises more questions than the number of questions. So we have a larger number of questions than the number of questions we had at the beginning. So, and we discovered that there are more things that we don't know. And the point is that all of this derivation was based on the assumption, on two key assumptions, or one key assumption, in a sense, which is the validity of the relations of thermodynamics out of equilibrium in an out of equilibrium situation. So we assumed that the equation rho plus P equal Ts plus mu n applies. This can be, in a sense, taken as a definition of entropy, in a sense. And then the TdS, also that the fact that also the differential equation has been used, this one, yeah. This differential form has been used. And one wonders whether this is true. I mean, whether in a non-equilibrium situation you may do something like this. So what is there anything, any theoretical or physics principle which ensures that this is correct? Well, that is a very good point, because I think that this will be, I would say, coped with in more detail by my colleague, that this theory, so that the relativistic thermodynamics equations which ensue from what I said, it is very well known that they have an important flaw, which is that they are non-causal. So if you write down these equations, by using these constitutive equations, then it is found out that in with some specific definition of U, which is called Landau frame, which means that U has been chosen in a special way, okay? It is known that these equations are neither causal nor stable. Pardon?
Is that legal? Can we use them if it's not causal?
No, but that is a workaround, which is the following, is that this workaround is based, indeed, on, it was found by Israel, one of the series of papers that I mentioned at the beginning of this lecture. The workaround is to admit that this expression of the entropy current is not entirely correct. And we must add something here. And by adding this something, Israel was able to formulate a theory in which was causal and stable. Okay? Now, there is more. Very recently, I think in the last 5, 6, 7 years, I don't know, that people, actually I heard this back in 2012 in a meeting, that they realized that the causality and stability of these equations depend specifically on the definition of a frame. So in the Landau frame, they are not causal nor stable. However, if you say in a suitable, even though I don't know this in detail, so I have not really studied these recent developments. It has been found out that this formulation can be causal and stable, provided that you have a special definition of the frame, so how to define the full velocity field at the beginning, and some relations between these coefficients are fulfilled, some inequalities. This is what I have understood from these developments. But this is not what I want to deal with in this set of lectures, because what I will be dealing with is something, I have mentioned this just because to tell you that these questions are not really trivial. So if you say modification of the entropy current means, for instance, that this relation might not be true in an out of equilibrium situation, okay? So you may find a definition of entropy which is more suitable in order to obtain causal relativistic causal and stable equations of hydrodynamics, but at the same time, that means that this equation cannot be, maybe it's not fulfilled in a general non-equilibrium situation, and it is just a case which just applies to an equilibrium situation, okay? But there is another more fundamental question. And the fact that in this formalism, you don't know how to deal with a very difficult problem, which is the following. So you have a fluid which falls apart and emits particles. The particles, it has been found out that they are polarized, okay? And this polarization depends on, also there are very strong indications that this polarization depends just on the fact that it is a fluid and not because there is some interaction between these particles. It just depends on the fact that it's a fluid which is close to local thermodynamic equilibrium. So how to calculate a polarization? So that is calculate the polarization means that you have to write the mean value of spin. Spin is a quantum observables, okay? So this is a vector. I mean, I will denote vectors by simply underline them, just because I will also, just to to introduce a notation, I will denote the operators with a hat, okay? Just not to confuse with classical values, with C numbers, or with mean values, okay? So you have to calculate the mean value of a quantum operator. So how can you do this in this formalism? Well, you can't do that. You can't do this, okay? There would be a way to do this by introducing a spin tensor density and deal with it just like the stress energy tensor. But the point is, there is another important point here which is very conceptual, and maybe I just want to bring this up, but not to discuss in detail, that the spin tensor density is something which is completely arbitrary. So it can be changed at will without affecting the general conservation law of angular momentum and energy momentum. Therefore, it is highly ambiguous. Yeah, it has to do with entropy in a sense. Yeah. So we have a practical problem. So how to calculate something which is inherently quantum from say if you start from a classical relativistic approach. Yeah? Okay, that is an important point. So we have to completely change, so erase what we have learned so far, okay, if you have learned something. So erase completely, and we have to start from scratch, okay? So we have to completely reset everything, forget about the classical approach to relativistic hydrodynamics and find a new one, which is more suitable to answer at least one of these questions. The second will be answered, but also the first. You will see that it provides an ambiguous way of defining an entropy current, an entropy density, to assess when and where it is possible to write an equilibrium. Yes, please.
If there is an ambiguity, how can we be sure that our choice is the best one?
Sorry?
If there is an ambiguity in choosing the entropy, how can we be sure that...
Ambiguity of what?
So that there is some ambiguity in defining...
The spin tensor density. Yes. I will show you that this derivation, I will show you that you can derive a value which is independent of the definition of spin tensor density. So you don't have to resort to a, say, classical relativistic method like the one that I have shown in the first part of the lecture, but you can do it without any ambiguity with a quantum framework. Okay? So the idea is to make a sudden transition from a method which is classical to a method which is quantum. Okay? So to describe a fluid in quantum relativistic terms, and not just in relativistic terms, okay? What? Yeah, that's spin tensor density approach, which, I mean, probably don't take it really yeah, it's something that is based on a classical, say, the inclusion of a new tensor, which is the classical, so if you wish, it's called spin tensor density. And this spin tensor density is used to define what is a spin of particles. But it has, it has a very fundamental problem that it is ambiguous because, maybe if you are interested in that, it is a problem called so-called pseudo gauge invariance of the stress energy tensor and spin tensor density, which makes it ambiguous. For instance, in the mostly used pseudo gauge, so-called, this is simply 0. So that is would be physically, so its physical meaning is still debated, and it would be really not good to make to calculate a physical observable based on this, yeah, right? So it is possible to calculate the polarization without resorting to the spin tensor density. That is a very important point. Okay, so after this motivation, let me then so after having reset everything, let us start really from scratch. Let us start from quantum mechanics, particularly quantum field theory, and ask ourselves how to formulate a problem in quantum field theory. After all, the collisions of heavy ions must be described by quantum field theory. Okay? Ultimately, they must be described as a quantum field theoretical problem. The point is that we don't know how to do that because we are not able to solve the equations of QCD. But in principle, this is a typical problem of quantum field theory. We have an initial state, two nuclei colliding, which can be described by a quantum state. Okay? So the state of the system we have the state of the system, which is described by either a pure quantum state or a mixed quantum state, if there is some ignorance on it, and which is called rho, the density operator. Density operator is the general concept which includes either the pure and the mixed case. So either the case where we know that the state is pure, or when we know that there is we don't know the state and we know the state with some probability. Okay? And then we have the equation of motion, equation of the fields. Okay? Which describe the dynamics. Okay? For instance, in QCD, we have equations I'm not going to write them, but we have equations, partial differential equations, like we have, let me, E gamma slash E the slash minus m plus A slash for the color fields, psi equals 0 for the quark fields. So we have quantum field equations, okay? That we put which must be solved. This is the typical approach in the so-called Heisenberg picture. The Heisenberg picture, you have the state is fixed. This is fixed. The state of the system is specified essentially by the initial configuration. Two nuclei colliding. So you write the state of the two nuclei before they collide, okay, where they are asymptotically this far apart. Okay, you can write the quantum state of these objects, and then the evolution is contained in the equation of the fields which depend on space and time. Heisenberg picture. Okay, the fields depend on space and time. The state is fixed. You may also reverse. You can also switch to the Schrödinger picture where the state evolves. This is in relativity. This is not natural framework, because the natural framework is to have something depending on space and time, okay, rather than space only. Although it might be useful under some circumstance to switch between these two pictures. Okay, so what is the state of the system in in the heavy ion collisions. And the state is simply two nuclei colliding very far apart. So you may imagine that this is a pure state, if you wish. If you know, for instance, what is the momentum of these two nuclei at infinity, with the infinite precision, then you may write down a pure state. But usually you don't do this. You write a mixed state, also, for instance, a scattering experiment of electron and positron, even if they are elementary particles. We know that the state, for instance, the state of the system is not pure, but this is mixed simply because you don't know the polarization of the electron and positron colliding. Okay? I hope that you are familiar with the notion of pure and mixed quantum state, right? Everyone? Okay. Now, so in principle, then, if we go back to this picture here, with two nuclei colliding, everything here is determined by the quantum state of these two colliding objects, okay? Which is known in a sense that we know that there are two nuclei with some momentum in some range, okay? So if we know that, and if you could solve these equations, then, okay, then heavy ion collisions would be a very, say, would not be really intriguing because it would be just machinery, right? You can put initial configurations to a computer and you get something out. But the point is that we don't know how to solve this, neither analytically nor numerically. And so we have to do something else. The point is the following. Here, that what we do then? We do the following. Okay, density operator. Then here I wrote something which is a very basic, this will be very useful in the following, very basic definition of what should be understood as a stress energy tensor that is used in heavy ion collisions. The stress energy tensor which is used in heavy ion collisions, which is what you usually what is usually put into the numerical codes, is an expectation value of an operator, okay? Should be understood as the expectation value of the operator stress energy tensor, which is formed out of the fields which are involved in the collision, like, for instance, QCD fields or the hadronic effective fields, anyway, anything, okay? This is a basic definition of an expectation value in quantum mechanics. So, expectation value in quantum mechanics is the trace over the product of the density operator and the operator that you are, say, simply that you are looking at, right? Now, if you write something like this, I put a 0 here because I now emphasize on time, but in general, then you would write for any operator that this is the mean value, okay, mean value of something, and in my notation this will be understood that every time you find something without, say, the hat, this is the mean value of some operator, which is, according to the basic, say, ingredients of quantum mechanics, is written as a trace of rho times the operator. This reduces to the so-called, to the well-known expectation value of some, in case of a pure state. So if rho is a projector onto the quantum state. Okay? Well, now the point is, suppose we want to calculate some relativistic hydro, therefore one should know, okay, should obtain what is the form of the stress energy tensor from the operators. But in order to do this, we should solve the equation of motion, again at the beginning of the problem. Now, what we can do is to make an assumption here, which is the following. First of all, we do not know, so we cannot solve the equations, but we may infer what is the quantum state in the Schrödinger picture at some later time. Let me explain more in detail what I mean. In the Heisenberg picture, okay, you can write something like this: T mu x. Also, I have a. Okay, there is a stick here, so I can. Yeah. Heisenberg picture, you can write that the operator is. You can write this as the propagator in time of this T mu x equals 0. This is an equation which should be familiar to in quantum mechanics, right? In the Schrödinger picture, on the other hand, T mu x0 is fixed, so we have something which does not depend on time, and what evolves is rho dt. But so it is just a reversing, you know, of just bringing the dependence in time to the density operator. What is left unchanged, of course, is the mean value is the same, right? Okay? Now, suppose then, now let's forget for a moment about the Heisenberg picture and set your mind, okay, in the Schrödinger picture. In the Schrödinger picture, the state evolves, so it might happen that at some later time, you may find a very good approximation of what would be the density operator at the time t, okay? So, rho 0, to be specific, is the density operator describing two nuclei colliding, okay? This is a quantum operator which evolves with time because it depends on the Hamiltonian, so it must be very complicated because it involves the Hamiltonian of QCD. But maybe you may find a situation at a later time where this, you know, you can find a good approximation of the density operator, okay? Go at a later time t naught. To be more specific in heavy ion collisions, this means the following. It means that we may find to be relativistic a hypersurface instead of time, because all of this can be rephrased in a more proper covariant framework. You may find a hypersurface where this density operator can be approximated. You may find a hypersurface where the density operator can be approximated by something which is, you know, simple, or something which is simpler, okay? It is not the exact one, because the exact one is given by this expression, but maybe you can find something which is, you know, very close to it. And this requires, of course, a physical assumption. And the physical assumption which is usually made in relativistic heavy ion collisions is that at some time, or at some hypersurface, it is written here, local equilibrium is achieved. This is something that you will find in many, very many articles, papers written about heavy ion collisions. So, and it is the basis, okay? It's the founding statement of the use of relativistic hydrodynamics, at least in the more traditional approach. So that local, so my colleague disagrees, that he will explain why probably there is something different. He thinks different in the respect, but say in the more common, I would say, the more common formulation, I would say, that the local equilibrium achieved means that this sentence contains a good approximation, it contains the idea of the approximation of the density operator with something which is simpler. So we need to find some density operator which represents the local thermodynamic equilibrium. Okay? So in other words, we have a hypersurface. Okay? Onto this hypersurface, which is an extension, a generalization of a propagation in time, we may obtain a good approximation of the actual density operator at the time defined by this sigma. So the actual rho would be, of course, what I wrote here. No, I can write it in the covariant. In covariant terms would be this one. And now all the symbols are involved are here. This is a Killing vector. This is the time Killing vector. This is a stress energy tensor. This is an integral of the hypersurface. And then you have plus I, same one. Okay, this is the actual one, but this is something that we don't know because it is, of course, in order to know this, you should solve the equations of QCD, and then you can do that. But we can obtain some very good approximation if we are able to define a local equilibrium density operator. So this is a translation in a quantum framework of the sentence that you find in papers saying that it is assumed that local equilibrium is achieved at some early time. That is the translation in quantum terms. Okay? So we have to find a density operator which implements the local equilibrium density operator. And if we do that, I can show you that we will be able to answer most of those questions. Most of the questions that you have seen in the previous slide. Okay? So how to define a local equilibrium? Well, I think that we have to learn first, which is the simplest, how to obtain a density operator which defines global equilibrium. This is a simpler problem. Let's start from the simpler problem. So global thermodynamic equilibrium. There are many ways, there are several ways to define global thermodynamic equilibrium. Let me pick up one which is the most suitable for our purposes, which is the following. Global thermodynamic equilibrium is defined by maximizing entropy under some very specific constraint involving conserved quantities. Conserved quantities is important because we know we want something equilibrium, so something which lasts in time. Therefore, we must select objects which are conserved. Otherwise, it would be not an incorrect definition. So, how entropy is defined in a quantum relativistic framework? Entropy has received, after a long, long time of discussions, statistical mechanics, a definition which must be framed, because it's a very important one. Definition, yes, there is a question. Yes, please.
I should have waited for the end of the sentence, but the question is if the arbitrariness that we have seen for the definition of the recurrent before is reflects here in the arbitrary of this definition.
No, this definition, no, that is not arbitrary. Okay. That is not arbitrary. No, this is a definition of entropy which is, say, unambiguous, okay, of total entropy. That is the definition of total entropy in a quantum relativistic framework. And this is the von Neumann, formula, so-called von Neumann formula of entropy, which says that, this is simply the extension to a quantum framework of the one which is perhaps more familiar. This one, okay, where you have the probabilities of each state. Okay, so if you have a set of possible states, entropy is defined as sum of a probability of, as a weighted sum of the probability of states of the logarithm of probability of states. Okay, and this is the quantum counterpart, right? Okay, so we want to maximize this with some constraints, some And which constraints I'm talking about? I'm talking about constraints involving the conserved quantities. What are conserved quantities in quantum relativistic framework? Well, I mean, at the beginning, okay, conserved quantities are defined by, first of all, the quantities defined by symmetries of space and time, and they are known as, you know that, the components of the four momentum operator, okay, energy momenta, they are conserved, okay, and also we have we have 6 more related to the symmetries of space and time, which are the angular momentum and boost operators, okay? They can be written as, in terms of expressed as a function of the currents, okay? They can be written like this, okay? P nu is this integral T nu. This is a definition which is independent on the hypersurface, okay? Whatever it is, sigma, because the divergence of these guys is 0. So since the divergence of T mu is 0, you can integrate P nu over any hypersurface and get the same thing. This is actually rephrasing the fact that P nu is constant. P nu constant in terms of, in a covariant term, means that this does not depend on the hypersurface where it is calculated, right? So it means that, means that if you take this one, or this one, or this one, any space like hypersurface you can think of, okay, it's the same. It will give the same result because the mu T mu nu is 0.
The area to some hypersurface has to remain the same, right?
No. No, you can take anything, any hypersurface you wish. There is a condition that the boundaries should provide no flux. That is another, because this is based on Gauss' theorem, okay? So P nu is a constant anyway, so everybody knows that, yeah? So that means that the energy and the momenta are conserved. It means that conserved means just that if I take this hypersurface of this hypersurface, which is delta T far apart, then you get the same result, okay? So independence of hypersurface is a synonymous of constancy. And it is a covariant expression, it's more covariant, right? That because time can be, it depends on the observer. Oh, the same applies to these guys, okay? J mu nu are constant, and if the stress energy tensor is properly chosen, if the stress energy tensor is properly chosen, which has something to do with the pseudo gauge invariance that we mentioned in the, earlier, then this integral is also divergence-free. So the integrand is divergence-free, means that the lambda of this is equal 0. Therefore, J mu nu is constant, okay? So you can think of integrating over any hypersurface and you will get the same result. So we have, and this is a basic quantum field result, that in the Minkowski spacetime we have 10 conserved generators. So we have 10 conserved basic observables, which are the integrals of the so the momenta and the angular momenta and boost, okay? So what I can do is that a global thermodynamic equilibrium situation can be obtained by enforcing So by looking for the maximum of entropy, so S max, and requiring that these constants, the mean value of these objects are constant, are given, okay? And how can we do this? We do this in mathematical method to obtain this is to formulate a constrained maximal or constrained extremal problem. It means that we have to look for the maximal function, which is the entropy, by adding some constraints. The method to do this is through the so-called Lagrange multiplier method. Lagrange multiplier method means that we take S and we add something which is simply a parameter, constant parameter, multiplied by the constraint, okay? So in this specific case, we have that the function I'm talking about is a function of the density operator is minus trace log rho. Perhaps I have written here, yeah, this one. So I can save some time. The function is minus, so this is just the entropy, plus, and then you see that I have used some Lagrange multipliers, which are constants, B mu, multiplying some constraint. These constraints tells us that the mean value of P mu is some constant P not mu, which will not become important in the following. And at the same time, I have other parameters multiplying the constraints related to the angular momentum and boost operators. Plus, I can also add something if I have some charged conserved. So I don't, on one hand, there are some space-size symmetries, but on the other hand, I may also have some inner symmetries, which are related to some conserved charge, like baryon number, or, well, I can add even color if I wish, would make things more complicated anyway, because it is a non-abelian symmetry, but I think of something like baryon charge and electric charge conservation, and then I can add some Lagrange multipliers also for these constraints. Now, this problem is well posed, okay? So I can find an extremal for the entropy with this constraint, okay? And the solution is the following. The density operator, which maximizes entropy. First of all, what is the variable to be changed in order to get the maximum? The variable is an operator, so it's rho. Right? This makes the problem at the beginning, it's not a single real variable, it's something more complicated. So it's a matrix in a Hilbert space. But nevertheless, this problem can be solved, okay? And the solution of this problem is the following. Rho is equal to an exponential. The appearance of an exponential is due to this fact that they have a logarithm here. The definition of it. Exponential of minus b dot p plus. So you see the Lagrange multipliers multiplied by the operators. And you have here 4 vector parameters, because they simply have to multiply p mu. And here you have an antisymmetric tensor multiplying the j mu. So that is a general solution. Omega colon j means omega mu nu, as usual in my formalism. Omega dot j means this one, double contraction with ordered indices. Okay, plus these scalars, zeta I, qi. Okay, the problem, okay, this is an exercise for the afternoon of tomorrow, not today, is to prove it. So prove that this is the solution of this problem. The problem is this one. We need to, you need to say, prove that if you maximize this function, irrespective of if you want to find the extremal of this function as a function of rho, then what you get is this as a solution. This is a very familiar form in a sense, because it reproduces all forms of global thermodynamic equilibrium that you may think of, okay? Actually contains many more that you probably don't know, okay? Let me show you an example. So, my statement is that this density operator includes all forms of global equilibrium in relativity. Let's try to prove this. For instance, you may think of a situation where, okay, these Lagrange multipliers, B and omega, are constants, okay? So how many independent constants do I have? 10, plus the charges, right, 10. The reason is that, of course, they should have been 10 because, of course, I have 10 generators. Okay, so I have 10 because I have a vector and I have an antisymmetric tensor. Actually, we can find that this vector must be time-like. The reason is otherwise that you get, in principle, can be also space-like, but you would get divergences everywhere. So let's forget about B not being time-like. So B and omega, 10 degrees of freedom, okay? Well, let's take some simple example. Omega equals 0, just to be very simple. So I don't have anything here. And I have B, and I take B equal 1 over T 0, 0, 0, where 1 over T for the present is just a symbol. So what I get is that rho becomes e to the minus p naught over T divided by some, of course, must be normalized, because the trace, yeah, that is something I should have included here. We must enforce rho to have a trace equal 1. That is very important. So this is one of the requests that I forgot to mention, that every density operator should be, I have a unitary trace. This is because the sum of probabilities along the diagonal should be 1, right? Unitarity request. So we have this one. What is P naught? P naught is the Hamiltonian. So therefore, what we have is that this, okay, that is also zeta equals 0. What we have is a simple e to the minus h over t, which is the most popular, I would say, the easiest density operator in quantum thermodynamics. This is the basic, say, density operator that is found in thermal field theory or in many, many problems, right? E to the minus h over t can be reproduced by choosing omega 0 and b equal 1 over t. And we discover, of course, that t has the meaning of a temperature in this case, right? Although we will see that the meaning of temperature can be found. Now, more complicated choices. Well, I can choose omega not to be 0, okay? But I can choose omega to be something like 0, 0, 0, must be antisymmetric. Minus something here. Antisymmetric. Oh, sorry. Here, yeah. Antisymmetric, so we have a minus here, plus here. And this gives rise, you can try yourself, to this kind of operator. This is an operator which is not very well known, but still it is a form of global thermodynamic equilibrium which represents a fluid in a global rotation around an axis with rigid field velocity. It is mentioned in the, I think that you know the physics, the famous book by Landau, Statistical Physics. This is mentioned in two places, okay, in this book. This operator is written down, okay. So one of the things that I have learned is that everything in statistical physics can be found in that book. Although even though with a very limited say expound, but it's, every topic can be found, and among them this operator. Okay. This is an operator representing a global equilibrium, which is the one of an object which has a constant angular momentum different from zero in the universe. And by enforcing the global equilibrium condition, it is found that this is a fluid which rotates rigidly around the angular momentum axis. Okay? And this is the quantum operator which represents this. You can find more, okay? You can find more equilibria, okay? In this formula. For instance, there is a kind of equilibrium which involves a constant acceleration along the velocity lines, which is quite an interesting one, which is related to the so-called Unruh effect. It's a very interesting equilibrium. However, that is not what I want to talk about, but this is just to show you that this problem can be solved, okay? That it leads to a formula. This rho is stationary, very important, so it does not depend on time, as you can find out, because B and omega are constant, and as well as P, J, and Q, because they are conserved. Therefore, this represents a situation where nothing changes, okay? You have no evolution. You have just that you can calculate, the mean value of operators at some different points in space and time, and in most cases, except the case where you have omega 0, they depend on x and t, so they depend on the space and time. But that situation is stationary, okay? So it does not change anymore. It's some problem, which is not then suitable to describe a situation like that in heavy ion collisions, because in the heavy ion collisions we know that we do not have global equilibrium, right? We have a situation which is highly dynamical. Therefore, what is the best, so this is not certainly the best operator to represent local thermodynamic equilibrium, which is not stationary, right? And I think that the time is now, so we will see this tomorrow, same time, right?
Tomorrow it's at
9 or no? Tomorrow is at 11:15, I guess.
I just think this.
Okay. Okay. Questions? Yes, please.